Hello everyone, we are Yue and Zhe. Our project is about exploring parallel t-SNE. Here's the roadmap for today. We will first introduce the t-SNE algorithm, then we will talk about approaches we use to parallelize the algorithm. In the end, we will discuss the results and conclusion. So, what's t-SNE? The full name is T-distributed stochastic neighbor embedding, which is a dimensionality reduction algorithm. Given X, which is a set of points in high-dimensional space, t-SNE outputs Y, which is a set of points in a lower dimensional space. The goal is that if two points are close in the input space, they should also be close in the output space. Here is the pseudocode for a sequential version of the algorithm. There are two main steps. In step 1, the algorithm builds a vantage point tree and compute the similarities between inputs. In step 2, you initialize the embedding result y and perform gradient descent for a number of iterations. In each iteration, you build a Barnes-Hart tree and compute the positive forces and negative forces and update y with the gradient.
Now, let's look at our proposed parallelization approaches. The first one is pretty straightforward. So in these three for loops, there are actually no loop dependencies between iterations. So we can simply apply OpenMP and use parallel for, and there will be no critical sections needed. Of course, we dig further into the algorithm, and we found the following. In step 1, when we are searching for k nearest neighbors, it uses Euclidean distance as a metric. And iterating through each dimension in the high dimensional point space is, of course, time consuming. And similarly, in step 2, for compute positive forces, it needs to iterate through the similarities of multiple neighbors found in step 1 to compute the total force. And of course, in the gradient computation and descent stage, we need to update values of a large memory contiguous array. And so these three use cases are perfect for FPMD with ISBC.
Our third approach parallelizes the negative force computation using 5 CUDA kernels. There are 3 important optimizations to make this efficient. First, we use a pre-allocated array to store the Barnes-Hart tree instead of using dynamically allocated memory. This way, we can traverse the tree using index instead of child pointers. Second, kernel 2 builds the Barnes-Hart tree iteratively with lightweight locking, implemented using atomic operations and memory fences instead of like mutex. Third, kernel 4 sorts embedding points such that spatially closed points are close to each other in the array. This minimizes thread divergence and improves the performance of kernel 5, which actually traverses the tree to compute negative forces. Based on this, we implemented 2 variants. In variant 1, we implemented 2 additional kernels for positive force computation and gradient computation, such that the entire step 2 executes on GPU. This reduces memory transfer to and from the GPU. In variant 2, we compute positive forces and negative forces in parallel, where positive forces are computed by CPU and negative forces are computed by GPU.
Now, let's look at how well our proposed parallelization approaches have performed. So here's an overview using one particular test case with 10,000 points. On the right is the step 2 gradient descent visualization, and on the left is the best runtime and speed up using 8 CPU threads. As we can see, our proposed approaches have achieved very good speed up to 60x on step 2 for the CPU plus GPU heterogeneous approach. For step 1, the best speed up came from ISBC plus OpenMP because we have not used a GPU for this step yet. And of course, as you can see on the previous slide, it's still slow with a larger test case. A future direction can definitely be to utilize GPU for k-NN search, such as using the phi similarity computation on GPU. For step 2, the best speed up came from CPU plus GPU heterogeneous computing. What we found here is that the overhead of memory data transfer between CPU and GPU is insignificant if there are sufficiently large number of points, meaning that those computations have high arithmetic intensity. This also means that the GPU-only version is actually slower in comparison because there are simply more arithmetic operations than the memory transfer overhead. So in conclusion, we have successfully parallelized Barnes-Hart t-SNE, an algorithm with high arithmetic intensity. Utilizing all compute power we have gives the best performance for this algorithm. That's all for our presentation. Thank you.